Hey there! Earth, our home, is a pretty stable place, but throughout its history there have been a number of significant events that, well, shook things up a bit. Some were so powerful they almost hit the reset button on all life. Today let's dive deep into some of the most intriguing and catastrophic Earth-ending crises. Approximately 66 million years ago, Earth experienced a catastrophe that forever changed the course of its biological history. An asteroid, estimated to be about 10 kilometers in diameter, struck what is now the Yucatan Peninsula in Mexico. This celestial intruder, traveling at an estimated speed of 20 kilometers per second, released an energy equivalent to billions of atomic bombs. The immediate aftermath was apocalyptic. The impact created a gigantic crater, now known as the Chicxulub crater, spanning 150 kilometers in diameter. This collision sent vast amounts of debris into the atmosphere, blanketing the Earth in darkness. This darkness, lasting possibly years, caused a dramatic drop in temperatures globally. With sunlight blocked, photosynthesis in plants became severely limited, leading to a cascading food chain collapse. Fossils and geological records from this period provide stark evidence of the devastation. The sudden drop in diverse species, especially the non-avian dinosaurs, marks this event's signature. Surprisingly, it wasn't just the massive creatures that went extinct. Many tiny, seemingly resilient organisms also disappeared from the fossil record. The Chicxulub Impact is widely recognized as the primary culprit behind the Cretaceous-Paleogene extinction event, one of the 5 major mass extinctions in Earth's history. Rewinding Earth's timeline further, about 2.4 billion years ago, we encounter a less violent but equally transformative event, the Great Oxygenation Event, also known as the Oxygen Crisis. Before this period, Earth's atmosphere was majorly devoid of oxygen, dominated instead by methane and other gases. However, with the evolution of cyanobacteria, or blue-green algae as they're commonly called, everything began to change. These tiny organisms had a remarkable ability: photosynthesis. By harnessing the energy of the sun, they could convert carbon dioxide and water into glucose, a process that released oxygen as a byproduct. Over hundreds of millions of years, these microscopic powerhouses proliferated, filling the oceans and atmosphere with increasing amounts of oxygen. While this may seem like a positive shift, the sudden rise in oxygen levels was disastrous for many of Earth's early inhabitants. Organisms adapted to the previous low-oxygen environment found themselves in a world that was suddenly toxic. Many anaerobic species which thrived without oxygen were driven to extinction or forced into specific niches where oxygen levels remained low. Beyond the biological implications, the oxygen crisis had profound geological effects. With the atmosphere's increased oxygen, methane, a potent greenhouse gas, began to react and form carbon dioxide, which is considerably less effective at trapping heat. This shift likely resulted in a cooling of the planet, potentially leading to one of Earth's first major ice ages. Iron in the oceans also reacted with the surplus oxygen, leading to the deposition of banded iron formations, layers of iron-rich minerals found in ancient rock formations across the world. Together, these two events, separated by billions of years, underscore the dynamic and often unpredictable nature of Earth's history, shaped by both internal mechanisms and extraterrestrial forces. About 252 million years ago, Earth bore witness to the most devastating extinction event in its known history: the Permian-Triassic extinction, often referred to as the Great Dying. This cataclysmic event wiped out an astonishing 90% of all marine species and 70% of terrestrial vertebrate species. The reasons for such widespread destruction are complex and multifaceted. Scientific investigations into this extinction event point towards a combination of events pushing the planet's biology to the brink. One major factor was the vast volcanic activity in what is now Siberia. As these volcanic regions spewed vast amounts of greenhouse gases into the atmosphere over thousands of years, global temperatures soared. The increasing warmth led to the loss of oxygen in the oceans, creating dead zones where marine life struggled to survive. Additionally, evidence suggests that the warming might have released seabed methane, a potent greenhouse gas amplifying the already rising temperatures. This, combined with acid rain resulting from the volcanic eruptions, severely impacted plant life, leading to a further disruption in the food chain. Fossils from this period paint a bleak picture. a world undergoing drastic change where complex ecosystems collapsed and once thriving species disappeared. From dominant synapsids to massive coral reefs, the swathes of life that the Permian-Triassic extinction silenced is a humbling reminder of the Earth's ever-evolving nature. Venturing back to a time between 720 and 635 million years ago, our planet underwent one of its most extreme climatic changes, the Snowball Earth hypothesis. This theory suggests that Earth was, at least on 2 occasions, entirely encased in ice, from its poles to the equator. Multiple lines of evidence support this chilling hypothesis. Glacial deposits, typically found in polar regions today, have been discovered in places now situated near the equator. Ancient rocks from this period show signs of glacial abrasion. Furthermore, specific chemical signatures in these rocks indicate a sudden drop in global temperatures. But how did our warm, life-supporting planet turn into a frozen snowball? Some theories suggest that this drastic cooling could have been instigated by the lowering levels of greenhouse gases in the atmosphere, possibly due to the proliferation of photosynthesizing microorganisms. These microbes might have consumed carbon dioxide, a major greenhouse gas, causing a significant drop in global temperatures. Once this cooling began, a feedback loop could have intensified the process. As ice reflects more sunlight than open water or land, the more the Earth's surface froze, the more sunlight it reflected back into space, causing even more cooling. Though the Snowball Earth might sound like a desolate, lifeless phase in our planet's history, it was quite the opposite. This extreme environment could have spurred evolutionary innovation. Some theories propose that the pressures of the Snowball Earth period led to the evolution of multicellular life, setting the stage for the complex web of life we see today. Far beyond our planet, in the mysterious depths of space, lie sources of immense energy capable of causing global havoc, gamma-ray bursts. These are the brightest electromagnetic events known to occur in the universe, emitting more energy in a few seconds than our Sun will during its entire 10 billion-year lifetime. GRBs are believed to originate from the core collapse of massive stars or from the merger of 2 compact stars such as neutron stars. When these cataclysmic events occur, they release a focused beam of gamma rays. If Earth were to lie in the direct path of this beam from a relatively nearby source, the results could be catastrophic. The Earth's atmosphere would initially absorb the intense high-energy radiation, creating nitrogen oxides that could deplete the ozone layer significantly. This depletion would allow harmful ultraviolet rays from the sun to penetrate our atmosphere, leading to a dramatic increase in UV exposure on Earth's surface. Such an increase could harm the DNA of surface-dwelling organisms, severely affecting ecosystems, especially phytoplankton, which forms the foundation of the oceanic food chain. Historical data points to a potential link between a GRB and a mass extinction event that occurred 443 million years ago, during the late Ordovician period. The exact correlation remains a topic of debate, but the potential danger of a GRB is a stark reminder of the universe's unpredictable nature. Around 74,000 years ago, in what is present-day Sumatra, Indonesia, a colossal volcanic eruption occurred. This wasn't just any volcanic eruption. It was a supereruption from the Toba supervolcano. The sheer scale of this eruption is difficult to grasp. To put it in perspective, the Toba eruption was approximately 5,000 times more powerful than the 1980 eruption of Mount St. Helens. The aftermath was equally monumental. The eruption spewed an estimated 2,800 cubic kilometers of volcanic material. Ash from the eruption was deposited as far away as India, covering vast areas in a thick, life-stifling layer. This massive output of volcanic gases, including sulfur dioxide, might have led to a global volcanic winter, a dramatic cooling period due to the reflection of sunlight by volcanic particles in the atmosphere. The Toba catastrophe theory postulates that this event had significant global consequences, especially for early human populations. The volcanic winter, which could have lasted several years, would have resulted in colder temperatures, reduced precipitation, and widespread vegetation loss, making survival challenging. Genetic evidence suggests a possible bottleneck in human evolution around this time, a significant reduction in population and genetic diversity. Some theories propose that the Toba eruption reduced the global human population to a small number of survivors from which all humans today are descended. While the exact impact of the Toba super-eruption on human populations and the global climate is still a matter of scientific debate, the potential power of supervolcanoes to alter the course of life on Earth is undeniable. In the relatively recent past, Earth experienced a solar event of such magnitude that, had it occurred today, it could have thrown our modern world into chaos. This event, known as the Carrington event, occurred in 1859 and remains the most powerful solar storm on record. Our sun, a constant presence in our sky, is far from stable. It's a bubbling, burning ball of gas, and occasionally it releases a massive burst of solar wind and magnetic fields. This burst, known as a solar flare, has the potential to wreak havoc on Earth's magnetosphere. During the Carrington event, British astronomers Richard Carrington and Richard Hodgson reported witnessing an incredible white light solar flare. Just 17 hours later, the Earth was hit by the resultant coronal mass ejection. Auroras, normally seen only in the polar regions, were visible as far south as the Caribbean. Telegraph systems across North America and Europe malfunctioned, with some even catching fire, demonstrating the power and reach of geomagnetic storms. The event is a chilling example of our vulnerability to space weather. In a world increasingly reliant on electronic communication and power grids, a solar storm of this magnitude today could result in widespread power outages, satellite failures, and communication breakdowns, with potential economic implications reaching into the trillions of dollars. And as always, I hope you enjoyed our video today. Thanks for watching.